In problem 8.63, we are given an op-amp circuit, as you see here. We have a voltage source, a resistor, a capacitor, and an inductor, and we have an operational amplifier right here in the middle. And we're asked to find the differential equation that governs the current through the inductor. So first of all, we want to make sure we recognize that if we assume this to be an ideal op-amp, there's a few characteristics that have to hold true. First of all, we're going to assume there's an infinite input impedance, which means that there's not going to be any current coming in to the positive or negative terminal here. The inverting, non-inverting input current is going to be 0. Also, because we have a negative feedback loop, we will assume that the voltage here at the inverting terminal is equal to the voltage at the non-inverting terminal, both relative to ground. And so in this case, since this is grounded, we know that the voltage here should also be 0 volts. Also, since there's no current coming into this, if we apply Kirchhoff's current law right here, what that tells us is the current through the resistor has to equal the current through the capacitor. And so if we go about applying Ohm's law right there, IR equals IC, and IR is just going to be VS over R, because we've got VS here, 0 there. The difference in voltage is just going to be VS over R for the current. And so that's going to equal C times the derivative of the voltage across the capacitor with respect to time. Then the question is, what is going to be the voltage across the capacitor? Well, we know on this left side of the capacitor, that's going to be at 0 volts of potential. And then over here on the right side, we'll just call that VL. And so here relative to here is 0 minus VL. So the current through the capacitor is going to equal C times the derivative with respect to time of negative VL. And VL, of course, is also going to be time varying. And so then the question is, okay, well, what is VL going to be equal to? Well, we know that for an inductor, voltage is equal to L times di dt, and I happens to be the current that we are looking for there. So VL equals the output voltage from the amplifier, which also equals L di dt. And so now if we plug that into what we have here, Vs over R equals C times the derivative with respect to time of negative L di dt. And so if we take this, we can pull out the negative L, that's going to be a constant. We can pull out the C and just divide the left side by L and C and multiply it by -1, and we get negative Vs over RLC, and this is going to just leave us with the derivative with respect to time of the derivative of I with respect to time. So that means the second derivative of I with respect to time is equal to negative Vs over RLC. And that is the characteristic equation that governs the behavior of this operational amplifier RLC circuit.